Lesson 2-6, Special Functions. Today we're going to identify and graph step functions, constant functions, and identity functions. First of all, a step function consists of line segments. Typically, the graph looks something like this, where you've got line segments that look like stairs. So we call it the step function. One example of a step function is the greatest integer function, and it's written using this notation. F of x equals the greatest integer of x, as I guess how I would say it, and it's got kind of 2 bars on either side of x with this funky bracket. That symbol means the greatest integer less than or equal to x. So if you were plugging in values for x here, here's some examples. On a number line, it's the integer to the left of the number. So if you are evaluating this for 7.3, the answer is 7 because you're looking for the integer to the left of the number. If you've got 8.9 in the greatest integer symbol here, the answer is 8. If you've got 0.6 or any decimal or fraction less than 1, the answer is 0. It's the integer to the left. So that's important to keep in mind. It gets a little tricky when your numbers are negative. Let me give you a few more examples. Negative 2.1, the greatest integer for negative 2.1 is negative 3. Negative 4.7 would be negative 5. Negative 0.3 would be negative 1. So it's the greatest integer that's less than or equal to x. So on the number line, it's directly to the left. Let's try graphing one of these. I'll show you in class tomorrow how to use your graphing calculator, but for today, let's do it by hand. So we're graphing f of x equals the greatest integer of x plus 3, and then we're going to determine the domain and range once we have our graph drawn. Okay, so I'm going to start by picking some x values to plug in. I'm going to plug in some negatives and some positives, and also some decimals so I can show you how those are graphed. Oh, probably should go to negative 1.5 second. Then maybe negative 1, negative 0.5, 0, 0.5, 1, and I'm going to have to scroll down a little bit, and then I'll just go to 1.5 here. This should give us plenty of values to graph. Okay, so our function is, maybe I'll move it down so I can see it. Here's the function that we're graphing. I'm going to move it just so I can see the table and the equation together. Okay, there we go. Okay, so if I plug in negative 2, I'm going to get negative 2. Negative 2 goes in for x. Negative 2 plus 3 is 1, and 1 is an integer, so the answer is 1. If I plug in negative 1.5, I'm going to get 1.5, and the integer to the left of that is 1. If I plug in negative 1 for x, I get negative 1 plus 3, that's positive 2. If I plug in negative 0.5, negative 0.5 plus 3 is 2.5, while the integer less than or equal to that is 2. When I plug in 0, I get 3. When I plug in 0.5, I get 3. When I plug in 1, 1 plus 3 is 4. And when I plug in 1.5, I get 4.5, and my integer to the left of that would be 4. And so you're evaluating, kind of like how you have to evaluate an absolute value. These symbols mean basically take off the decimal and go to the integer to the left. Okay, so anyway, let me show you how to graph this. You've got negative 2, 1 is on the graph. Negative 1.5, 1 is on the graph, so that's right about there. Negative 1, 2 is on the graph. Negative 1.5, 2 is on the graph. 0, 3 is on the graph. 0.5, 3 is on the graph. 1, 4. And 1.54. Okay, now these are not all of the values on the graph. These are just some of the x values that I decided to choose. Let me fill these in and show you what the graph really looks like. If I were to plug in any x values in between negative 2 and negative 1, my value would be 1. And so this part of the graph is just a straight line going across, and then I need an open circle here because as soon as I plug in -1, my value jumps up to 2. This will be a horizontal line just going in between -1 and 0. Again, with an open dot once I get to 0, because at the moment that I plug in 0, my values jump up to 3. Anything that I plug in between 0 and 1 are going to give me an integer of 3. So I know that these values are on the graph. Open dot here because 1 doesn't go to 3, 1 goes to 4 now, so the function jumps. Anything that I plug in between 1 and 2, like 1.7, 1.8, whatever, all of those values will stay at 4. And so I've got a horizontal line in between 1 and 2 at 4 here, open circle. And this graph is repetitive. It's basically the same pattern over and over again, where you've got a closed dot on the left endpoint, horizontal line, and then an open endpoint at the right value. Okay, so this goes on forever. I also need to fill in some pieces of the graph here. And this is what a step function looks like. Now your graphing calculator is able to produce these graphs, but the bad part is your graphing calculator doesn't give you the open dot or the closed dot. And so you have to understand kind of how it works as well. You have to understand how to do it by hand so that you can get the same graph. Now let's go over domain and range. The domain of this function is actually all reals. If you look at the x values, I can plug in any x value I want into this function. There aren't any x values that are skipped on this graph. So my domain is -infinity to +infinity. The range values, my y values are a little bit limited here. If I look at the y values, I kind of just go along the y-axis here and figure out where my y values are located. I don't have any y values in between the integers. I have y values at 0, y values at 1, y values at 2. And so the range is a little bit weird here. It's, you can't really use an interval to define the range because it jumps from 0 to 1 to 2 to 3. And so when you describe your range, I would just write that the y values or the range values are all integers. That's where the pieces of the graph are located on the y-axis, all integers. Okay, we're done with this graph. Let's try a word problem and see what happens with this graph. A recycling company pays $5 for every full box of newspaper. Draw a graph that shows the amount of money for the number of boxes brought to the center. So we have to remember that we get paid $5 every time we have a full box of newspaper. Filling it halfway there or 3/4 of the way there doesn't make you any more money. Okay, so along the x-axis, I'm going to have the number of boxes. And along the y-axis, I'm going to have the money. Okay, so when I fill one box, actually I can't even fill half of a box here. I won't get paid. So I need to start with 1. When I fill one box, I'll get paid $5. If I fill anything in between 1 and 2, I'm going to stay at $5. When I fill 2 boxes, I jump up to $10 because I get paid $5 for every full box. So when I bring in 2 boxes, I'll get paid $10. Any amount after that, I'm going to still get paid $10 until I fill that 3rd box. At that point, I'm going to jump up to $15. I didn't really make my graph appropriately here. I'd probably want to go by 5s on my Y scale since I'm getting paid $5 for every full box of newspaper. You can kind of imagine what the graph would look like. From 1 to 2 boxes, I get $5. From 2 to 3, I get 10. From 3 to 4, I get 15. From 4 to 5, I get 20, and so forth. And you get this step function. But the steps are spaced quite a bit farther apart here. If you wanted to list domain and range, your domain would start at 1 and go to infinity technically, I guess. You could fill infinity boxes, and then your range values would be multiples of 5. You're only going to have y values every 5, 5, 10, 15, 20. So there's another example of a step function. Okay, a couple more functions to talk about. One is the constant function, and the other one is the identity function. If you think about slope-intercept form, y equals mx plus b, if m is 0, the slope is 0, then all you have is f of x equals b, some number. This is called the constant function, and when you graph them, remember that lines that have a slope of 0 are horizontal. And so you just get a horizontal line at that value, whatever b is, going through the y-intercept. When m is 1, when the slope is 1 and the y-intercept is 0, then you get the function f of x equals x, or y equals x. This is called the identity function. It means no matter what you plug in for x, the input and the output are always the same. And so you get ordered pairs like 1, 1, 2, 2, 3, 3, and so on. F of x always equals x. Okay, let me show you these two graphs, and then we're done. The constant function, here's an example. F of x equals 5. It's a horizontal line going through 5. Y equals 5. There it is. Remember, f of x just replaces y, and so you can always think of this as y equals 5. The slope is 0. There is no x here, so the slope is 0. The y-intercept is 5, and you've got the horizontal line. The identity function is y equals x, or f of x equals x. And I just described that one on the last page. So points like 0, 0, 1, 1, 2, 2, 3, 3, 4, 4. Those points are on this graph, and so it just makes the diagonal with a slope of 1, up 1 over 1. All right, I'd like you to try these graphs on your own. The first one is practice with the greatest integer function, and the second one is just a constant function.